This is the first video on Chapter 12. Chapters 12 and 13 are being taught together. Chapter 12 focuses on data gathered through one sample, be it means or proportions, and Chapter 13 focuses on data gathered through two samples where we're trying to compare data for two different populations. Section 12.1 focuses simply on means and builds on some of the tools that we put together in Chapters 9, 10 and 11, but to be frank, there's not a lot new here. We're talking about the difference between Z procedures and T procedures, and while it says it at the head of the table here, I would hope that if I asked you what the difference is at this point, you would know that we're using T procedures when we don't know sigma. Now, when we did know sigma, we did significance tests and confidence intervals using a Z test statistic. This is what we did in Chapter 11. You were just tested on this, where the test statistic is x bar minus mu over standard deviation of x bar, which is sigma over root n. And we did confidence intervals previously, where we had x bar plus or minus a certain number of standard deviations, that certain number defined by z star. Well, we take away the somewhat unrealistic assumption that we know sigma, and we've done this. We did t intervals. We took away sigma and we dropped s in its place, and as soon as we did that, we were dealing with t star instead of s and dealing with t distributions instead of standard normal distributions. Well, the logical next step is then to do significance testing, which still involves a test statistic, which tells us how far away a piece of data is from our expectation, or the means from a sampling of data is from our expectation. And so now we have what's called a t-statistic, t-test statistic, and it's x bar minus mu, but you'll notice we've taken away s, and we do that, we now use t. So we still have a test statistic here, which we'll still use to gather a p-value, and when we get to the examples, you want to pay attention to how we do that, because it is slightly different. But the meaning is the same. We have a test statistic that indicates, helps us understand how unusual our data is. The bigger t is, positive or negative, the more extreme our data is, or the more surprising our data is. Now, this is an introduction to what you see on the formula sheet, and what you see down here at the bottom of the sheet is how the formulas are presented to you on the formula sheet. So we're using test statistics and confidence intervals for single sample or one sample data, and you need to get used to the idea, should you need it, about how the formulas are presented to you. So we have a standardized test statistic that's T or Z, and the formula sheet doesn't tell us whether it's T or Z. It just tells us that we're going to take a statistic minus a parameter divided by the standard deviation of the statistic. It does give us some guidance down here about what those standard deviations look like for means and proportions, but you still need to be careful about how you go about the work. So we have these test statistics, Z, equals x bar minus mu divided by sigma over root n. But in this lesson, in section 12.1, we're adding t, which is also x bar minus mu, but divided by s over root n. And in section 12.2, we'll get to proportions. We'll be back to z, but it'll be p hat minus p, estimate minus parameter, divided by standard deviation, p hat times 1 minus p hat over n. And you'll notice that what I wrote up there doesn't look exactly like what's on the formula sheet, so you have to get used to the need to replace sigma with s and replace p with p hat where necessary. Confidence intervals, similarly, it gives you, we get a rough outline here of what the formula is. So for a z interval, we have x bar plus or minus z times sigma over root n. A confidence interval is a statistic plus or minus a critical value divided by the standard deviation, or times the standard deviation. If it's a t interval, it's x bar plus or minus t star, I've done a star here too, times s over root n. And when we get to intervals for proportion, it'll be p hat plus or minus z star again, times the square root of p hat times 1 minus p hat over n. So the formula sheet presents things as shown in the lower right here. You need to be comfortable with how to use that formula sheet should you need it to come up with the proper test statistic or confidence interval. Conditions here aren't changing, so we're dealing with means right now. So we have an SRS. You need to remember now, let's get more sophisticated about this, that you may or may not be given an SRS, and that goes to your ability to generalize to the population. So you may want to note that. Don't simply assume an SRS. Point out that it might be missing and that that limits your ability to generalize. Independence, we had a rule of thumb that said if the population was greater than or equal to 10 times the sample size, that was an adequate way to check for independence. Probabilities don't change if you pull a piece of an observation from a large population without replacement. But we can also use a common sense argument here sometimes about independence. So the rule of thumb might apply, but it might not work perfectly in all situations. Normality then, we'll recall that if the population is normal, we're in good shape. We can use the central limit theorem if n is greater than or equal to 30. But if n is small, then we need to make a graph, a histogram, a box plot, or a normal probability plot. And recall the argument we're trying to make is that once we look at the data, there's little skewness, no outliers. And if that's the case for that small sample size, it's a bit of a stretch of logic, but we're going to make an argument then that the population we're pulling data from might be approximately normal, and we'll proceed. Another thing you'll have to do, and you'll see this in the examples in a separate video, you're going to have to be able to distinguish between a t-test and a paired t-test. And remember, a paired t-test, we pull data from a matched pairs design. So you need to recognize a matched pairs design and then make the logical next step that the test we're going to do is called a paired t-test. In a matched pairs design, we get data in possibly 3 different ways. We have matched subjects where we're comparing a piece of data, a score of some kind, an observation of some kind for those 2 matched subjects. We might be comparing 2 treatments for 1 subject, or we might be looking at before and after data for a subject. And in all of those cases, the parameter, this is in the p-step of phantoms or the p-step of panic, is mu little d. And it's important that you recognize it's a slightly different parameter, and it's called mean difference. When we get to chapter 13, we'll talk about something called difference of means, and students frequently confuse those two. So this is all based off of 1 sample where we take 2 pieces of data and compare them for a single sample. When testing, we're testing mu d, the mean difference, as opposed to just mu, a mean. Hypotheses are, in a significance test, mu d equals some value, and the alternative is mu d is less or greater or not equal to some value. All those little details matter. It's still based off 1 sample, so we still use 1 sample t procedures. And when you get down to your conclusion, all these details matter. You're going to reject or fail to reject the null and talk about the fact that you do or don't have evidence that the mean difference is whatever your alternative hypothesis is. Now, you'll see examples of this in the examples video, but pay attention to those details. Lastly here, a reminder, when you use t procedures overall, we have to be careful about sample size and skewness related to that. So the t procedures are robust against non-normality to a degree, except when outliers are present or when the data is strongly skewed. So they're robust for slight skewness, but not for a situation where there are outliers or a lot of skew. And recall that if something is robust, that means the findings, the outcomes, the calculations don't change as a function of heavy skewness or outliers. So the use of the t procedures here is outlined for you. This is directly from your book. And there are 3 situations here. 1, when n is less than 15. Second, when n is greater than or equal to 15 but less than 30. And then a 3rd sample here when n is greater than or equal to 30. So even for t procedures, when we have large samples, the central limit theorem applies. When the sample size is between 15 and 30, then we can we can use the procedures except in the situation where we have outliers or strong skewness. And then when the sample size is quite small, really we can't handle outliers or much skew at all. And that's what you're going to be looking for when you have a small set of data and you're graphing it for the normality check. Now lastly, you should take some time and do this right now. Go to your calculators. You actually have t-tests and z-tests on your calculator. For the 84s, it's under tests. For the 89s, it's under F6 tests. And again, you'll see z-test and t-test. You'll see the same data or statistics choice when you get in there. So if your data is all in a list, you're going to use the data option. If you have the details you need, X bar and sigma, X bar and S, you use the stats. It's important, you'll see at the bottom, you have to pick the proper alternative hypothesis. And when you do that in your calculator and try this on the examples we go through, you'll get the test statistic and p-value. It'll come out to you. But remember, even though your calculator is giving it to you, you must show calculations when you do the work. You can't simply write down the test statistic and p-value. I will say it again, it's that important. You cannot simply write down the test statistic and p-value. You have to show that you know where those numbers came from. On the AP test, it's impossible to get full credit without showing your work, and that'll be the case on our tests as well. So section 12.1 is really on t-tests and t-intervals again. T-testing is the key difference. Paired t-tests are emphasized a bit, and you'll see that in the example video that's separate.